Alright, let's talk about digital processing and display. So, here's just an overview, and this is going to track pretty closely to the ARRT outline. So I've even got this reference to the ARRT outline in the PowerPoint. And just so you know, there's about 12 questions on the board that deals with this, right? So that, to me, as an instructor, as someone who might be taking this test, it signals to me that I don't need to be a computer programmer to do well on this. I need to have basic terminology and understand how the terminology relates to what we're doing. So we'll be talking about histograms, grayscale, edge enhancement, equalization, smoothing, and electronic masking. Okay? Now, masking is a pretty broad term, right? There's a bunch of different kinds of masks that we can apply to something. So we'll really just talk about one kind of electronic mask that I believe the CR systems and DR systems use. So here's an overview that was provided by Fuji of how exposure data recognition works. So that would be the kind of the broad term. And you'll notice of all this stuff, the thing that we're looking at most closely is going to be histogram analysis. So there's a lot of things that the computer does to recognize the image, but the board really wants us to just be familiar with the histogram analysis and then the stuff related to the diagnostic image creation. These things prior to that are going to tie in more directly to computer science, and it kind of goes above and beyond the expectations of a radiologic technologist. Nevertheless, be aware that the computers are doing a lot to get as a diagnostic image. So, what is a histogram? I got this from Fahlberg, Chapter 7. It's a graphic representation of a data set. Okay, so let's unpack that a little bit. It's going to look like a bar graph, right? And on this bar graph, we're going to have the pixel values, and it's going to be all the various ranges of pixel values. And from that, we are going to then apply edge detection and rescaling algorithms, right? So along this bar graph, the x-axis is the amount of exposure. So as we travel further and further along the bar graph, in the x direction, we're going to see kind of a gradual peak of exposure that will fall off, and the y-axis is going to be the incident of pixels for that given exposure level, right? So what this is saying is if we draw an XY graph, we're going to see something that looks like this, only it's going to be represented by a bar graph. Does that make sense so far? So it is a graphic representation of the data set. So here is a picture again from Fujifilm of what this histogram looks like. So we have this detection area that was then required. It's a required area for diagnosis, and the computer is using this frequency and input to start to figure out what exactly, where an edge is, where the information that's important resides. So it's interesting too to look at the kind of various curves that occur on this. It's kind of got two mountain peaks on it, right? 1 and 2. So what this graphic is trying to show us is that this input range right here is being processed to give us this image where we've got all of the brighter stuff, or all of the areas like of the lung where the image the X-rays have bombarded the IR. Those areas are kind of overly bombarded to where there's this black spot of non-diagnostic material, and then it goes and it averages that along with this area where the stuff that's really, really white, where there was not enough penetration. And between those two, it results with this image, right? So the computer is going to analyze the histogram using processing algorithms, right? and it compares it to a pre-established histogram specific for that body part, right? So when we tell, as a user, when we say this is a chest x-ray, that's significant because it's going to take that bar graph and it's going to relate it to other chest x-ray bar graphs. And there should be some kind of similarities in the way that the exposure works. Like, for instance, there's it knows that it's going to see a peak and a trough, right? And it's going to try to relate those two using special algorithms or recipes. One of the ways it does that is it's going to suggest that there's certain values of interest, right? And we can actually change these values of interest after the fact. But the stored histogram models are have values of interest, right? They're going to have, like, for instance, with that chest x-ray, they're going to have a peak and a trough. And so those values of interest are going to relate to how the displayed image is eventually generated, right? So it's going to look at the histogram for the image that you generated, right, for the data set that we have. It's going to compare that back to a histogram that's kind of like a template, right? And between the two, it's going to decide what needs to be included in the displayed image. So part of how it does that with the value of interest is called rescaling. And generally this is done automatically. And this is kind of where the really, really dirty stuff happens, if we're honest. This is where dose creep occurs, is in rescaling. So the machine is going to automatically rescale for that data set based on a histogram model. So it can take a film that's way, way overexposed, compare those frequencies back to an appropriate exposure, and rescale it down to an appropriate exposure level, even if it's been overexposed or underexposed. When it's underexposed, we would expect to see some quantum model, right? We would expect to see some graininess on the image. But it can even smooth over that just a little bit. Okay, so we'll talk about how it smooths over those kinds of things. So here's an example from that website I showed y'all before of a skull film taken with, so this would be an underexposed technique here. This would be about appropriate probably for skull radiography. And then this is about 10 times the appropriate technique, right? And even with the underexposure and the gross overexposure, we have, because of rescaling, we have images that look very, very similar. Grayscale from Bouchon. The range of values over which a system can respond is called its grayscale range or dynamic range, right? This was going to relate right back into latitude, okay? We talked about grayscale some in the past, and we related it to technique and contrast in particular because grayscale is tied not just to latitude but also to contrast. And that was kind of one of the connections I wanted us to make on this last quiz, is that if I'm varying the way that this thing can perceive different contrast levels, I'm also going to, in both film stream and digital systems, affect its dynamic range, right? And we'll unpack that because there's a bunch of different ways that we can apply grayscale to what we're doing, and there's ways that we can adjust the grayscale too. So, the ART board asks us to talk about bit depth, right? So within a pixel, there's going to be a number of bits that are used to indicate the attenuation value for that pixel. What on earth are we talking about? Within each pixel, there is going to be a bunch of little places that information can be stored. And that information is going to be stored as a 1 or a 0, right? Now, to record an attenuation event or an attenuation value, the pixel is receives some amount of exposure, right, to either a luminescence or to an actual direct exposure from an X-ray, right? And then it records that in these bits, and it has only so many bits to record that. So if you can imagine these exposure ranges, they're going to be lots of decimal points behind them, right? There's going to be lots of decimal points. Its ability to indicate the value there the precision with which it can indicate the attenuation that the energy that the X-ray had, right, is going to be housed in these bits. Okay, so the number of bits within the pixel is going to tell us how accurately or how much precision it can digitize that analog signal. Okay, and we're going to call that bit depth. You could also call it, I guess, bit number, just the number of bits in that pixel. And then a lookup table. So the raw data that we get when we make an exposure is going to be pretty flat, pretty like low contrast kind of stuff. So we have to automatically alter it to increase the contrast. And the lookup table is going to provide the algorithms to alter the brightness and grayscale of that digital image. So here's an example of how that lookup table functions, right? This should look somewhat familiar because when we were talking about film screen stuff, we talked about that S-curve of sensitometry, right? So we have this curve of the film screen system, and between the toe and the shoulder of the curve, this is kind of the sweet spot. This is where an appropriate exposure can be recorded, right? What this is telling us is that with the initial kind of just the CR or DR plate, we're going to have a pretty flat line from going from one corner to the next, right? But what this lookup table is going to do is it's going to start to put in some kind of curve to it, right? And generally that curve will look somewhat similar to the curve that we see in, like with a toe and a shoulder in film screen. So this is one place where digital and film screen are kind of similar. So I actually have drawn this in here inappropriately. There should be a toe and then a rising part and then a shoulder, right? To the way this lookup table functions. And it's going to just make little tiny tweaks to it, all right? But it's giving it a little bit more contrast. Again, this is something where digital, like Photoshop and programs like that can give us a little bit of help. This graphic actually comes from a site that's dedicated to color digital photography, right? So it has the RGB scale, like red, blues, and green scale, that it's applying to the image. It's applying to the data to make it appropriate for display on a monitor, right? That same stuff is what we're doing in X-ray, right? We just are not taking it maybe to the degree that a digital photographer is, right? We don't need to. Honestly, our work is enough, and so we are letting the computer automatically do a lot of this stuff for us. So, edge enhancement. This is after we've done all our histogram analysis. We are going to allow the computer to apply some edge enhancement algorithms to the image. And this is going to actually be what generates, it's going to be the beginning of generating a diagnostic image. So y'all may remember, if we're working on that Fuji system and we're watching as it kind of develops the film, every now and then we see like the ghost of an image appear and it looks really gray, and then it does a flash, and then all of a sudden we have what looks like a diagnostic picture. All of this stuff is happening in between that gray place and that flash, right? So the gray place would be that initial image that we got that just is a recording of bit depth, and it's going to be a fairly flat image, right? And then in that flash, we're doing edge enhancement, we're doing rescaling, we're doing a lookup table analysis on all of that. All of that's happening in that flash, right? So the computer's doing a lot of work really, really quickly. But edge enhancement basically is going to improve the visibility of small, high contrast areas on the image, but of course it might also increase the image noise, right? So if it's going to do something to help us see these small, high contrast areas, we would expect it to increase image noise, right? Both those things seem interrelated. And again, if we were working on Photoshop, we could pull up and maybe I'll even try to produce a short video on like my iMac of what happens if I zoom in on a little tiny area of an image, and so I've zoomed in a whole lot on a line that's like maybe the cheek of someone's face, right? And now I'm going to apply edge enhancement to that. The more and more that I try to enhance this edge like this, eventually I'm going to start getting little things like this out here, right? And that's all this is saying. It's going to increase some noise. Equalization. The board uses the term equalization, and this is a method of contrast adjustment, right? Where it takes pixels that are in the same basic area and it starts to bring them more closer to the same color, right? So it's going to increase the contrast of the entire image. We can't just go in and pinpoint an area and try to equalize it. It's going to go across the entire image, and we can manually equalize the image. So it increases the global contrast, especially when the data is represented by very close contrast values, right? So I have this pixel here that's about a 1, and this pixel here that's about a 1, right? The attenuation values are very close. Equalization is going to bring them that much more in alignment. And so it's also conversely going to allow areas of local contrast to gain a higher contrast. So this area over here was a 1, this was a 0. When it does that, it's going to make them that much more. It's going to make the pixels around them closer to those values as well, and enhance that contrast. And one way to think about this is that it's going to spread out the most frequent intensity values. So if we're looking at the histogram, right, and we've got a histogram that's all these little lines here, right, and they're all fairly close to each other, the way equalization works is it's going to spread out those areas, right? So it's going to enhance the gap between them, and I can actually show us what this looks like on a digital. So maybe we can see. So here we have a fairly flat image, and if we look at the histogram, all of the values are pretty bunched up along the S curve, right? They're all in the middle of the S curve because that's where we want them to be, right? They're not at the toe, and they're not just at the shoulder. They're kind of spread out across the exposure range. But what we're going to do when we do equalization is we're going to put some gaps between them, right? We're going to put little gaps between them, and that's going to give us a picture that has higher overall contrast. Okay? That's equalization. Smoothing. So this is going to be a post-process technique that suppresses image noise, especially quantum noise, right? And of course, it's going to degrade spatial resolution because it's going to smooth things out, so it's not, the resolution between different spaces on the film is going to be lost. Related to that very closely is electronic masking. Generally, if we're applying a masking layer to an image, we're doing it to smooth out the edges on it, right? So it's going to kind of blur the edges some. And why would we want to blur out the edges? Well, as we're applying a mask to a film, it may just help the eye to better perceive if we just kind of smooth out the noisy places and allow a more continuous kind of image, right? So here's an example. We would call this a Gaussian blur, right? And so this would be an electronic mask that we've applied to an image. And if we see up here, this is a more accurate representation of what we received. That's the digital signal that we received, right? But it has a halftone quality to it, right? It's almost like something out of a newspaper. Can y'all see the little dot pixels on it? So we're trying to figure out what of that is noise and what of that is good signal, right? But some of it's noise, some of it's signal, and the human eye is actually distracted by the lines and by the chattery nature of that image. So blurring, applying an electronic mask or a Gaussian blur to it is going to give us a more kind of uniform image. but we've lost some spatial resolution as a consequence. So if I zoom this in, right, let me see if I can get my zoom tool going. Yeah. All right. Now we're looking at the little pixels, right? I've blurred them out through here. All along this area of her eye, I've blurred that out, right? If I go up to the image above, I can see now the spatial resolution there. Does that make sense? Okay. So here's a quick review question, right? The range of values over which a system can respond, what are we going to call that? The range of values over which a system can respond. It's grayscale, right? So I went back to our last discussion of grayscale and talked about how high KVP equals a low contrast, which is also a long grayscale, right? A low KVP is going to give us a higher contrast and a shorter grayscale, but it's still the value of interest over which our imaging system can respond. So we've related it now not just to the IR plate, but also to the technical factors that are influencing the image receptor. Questions about that? Okay. Let's talk about image display. So an overview here is we're going to talk about viewing conditions, like just how we should be looking at these pictures, what should be the ambient light levels, spatial resolution, and then window level and width functions. And a lot of this stuff is going to tie directly into our discussion of CT next year, right? Window width and level is a big part of how CT works. So a lot of what we're talking about right now, all of it, I've been going back to my CT books some too, because digital radiography is kind of the step-off point between radiography and CT for a lot of reasons. So viewing conditions, generally we're going to have some awareness of the ambient light in the room. Generally we're going to maybe turn the overhead lights off, right? And we want to be aware of where the monitors are placed, how we can best view the monitors, because how the ambient lighting in the room can affect what we would call soft copy viewing of the digital image, right? What is soft copy image viewing? It would be anytime we're looking at it on a computer screen, right? If I've printed it out, if I've printed out a film and I'm hanging out on a whiteboard, that would be hard copy viewing, right? But the bulk of what we're doing we would call soft copy viewing, and that means we need to be aware of both the amount of pixels, like the pixel value of or the display values of the monitor, and also the kind of lighting that's around the area where we're viewing. Luminance is going to relate to the monitor and the viewing of the monitor. And y'all, I believe the Semtex slideshow should have had some of this information in it as well, so some of this may be a repeat. But luminance is just going to be the measure of the light intensity that the monitor can produce, okay? And it's generally expressed in candela per square meter. And monitors that we use in radiography should be in this range of like 300 to 500 candela per meter squared. Most computer monitors are well above that now. Spatial resolution. Again, spatial resolution in digital imaging is going to be limited to the size of the pixel, right? And that's not just the pixel value of the IR now, but also the pixel value of the monitor, right? Because what we've done is we've passed this signal back and forth from digital to analog, analog to digital, and now it's back at our monitor and it's being represented by pixels on our monitor. And if we have a monitor with gigantic pixels like an old dot matrix printer, we're not going to be able, even if we had a really great set of images and set of algorithms that we applied to it, we've now constrained our ability to see what we need to see by the monitor. So a lot of radiologists are going to be using like 2K or better monitors, right? Because that has a high number of pixels within the monitor. Okay, so spatial resolution is tied back to pixel size and the density of the pixels on the film, on the image receptor, right? So the greater the number of pixels in the matrix, the smaller their size will be. And the pixel density is just a way to talk about the number of pixels per unit area, right? Now pixel pitch is another way to think about that. It's just going to be the spacing measured from the center of one pixel to an adjacent pixel, right? And it's the edge of that adjacent pixel, because we could, in theory, we could have these pixels overlapping and then we would have a seamless kind of spatial resolution. We've yet to develop that kind of technology. But that's why we measure, for instance, let me get my little drawing tool, why we measure from the center of one pixel to the edge of the other, right? Because there's always going to be this little gap here, right? So, increasing the pixel density and decreasing the pixel pitch increases spatial resolution. Okay? Increasing the density, decreasing the pitch is going to increase spatial resolution. Interestingly enough, this exact same principle is true in CT. Computed tomography uses things like pitch and pixel density. So file that away in the back of your mind. We'll be talking about it this time next year when we talk about CT. Decreasing the pixel pitch and increasing the pixel, decreasing the pixel density and increasing the pixel pitch will decrease spatial resolution, right? So decreasing the pixel density, there's less pixels in the area, and we've got a wider space between them. We're going to have less spatial resolution. Let's talk about window, level, and width. This also will apply in computed tomography. A window level sets the midpoint of a range of brightness visible on an image. We'll look at a graphic display of this in a moment. But just know that increasing the window level is going to increase the image brightness. Decreasing the window level is going to decrease the image brightness. Okay? Window width is going to adjust the array of contrast that we can see at that given window level. So window width is going to be the center point, more or less. It's going to be centered on the window level, and it's going to be a width across that level at which we're adjusting the contrast. So a wide window width is going to be a long scale of contrast, and a narrow window width is going to be a shorter scale of contrast. Okay? Here's a graphic representation of that. We know what the attenuation level is for various kinds of tissue. So we tell the computer, I want the window level to be right here, about at the level of soft tissue. So above that of water. And I just, a little kind of aside here. This graphic comes from computed tomography, right? In computed tomography, we set a Hounsfield unit as 0 at water, right? The attenuation value of water, we're going to say, is 0, right? Anything less dense than water is going to be in a negative range. Anything with more density than water is going to be in a positive range, okay? So, for instance, on the Hounsfield scale, air is equivalent to negative 1,000, right? And if we go up to bone, it's equivalent to a positive 1,000 or thereabouts, okay? So when we're setting a window level, we're saying I want to be centered on this area right here. And generally it's going to be in a positive range, okay? Somewhere around 100 perhaps. And then when we set the width, we're saying I want this these to sample from these areas above and below. Okay? And that's going to be what gives us our sample here of shades of gray. So, quick review question. Decreasing the pixel density and increasing the pixel pitch does what? Decrease. Good. It's going to decrease the spatial resolution. So the greater the density of the pixels in a matrix, the smaller their size, and the higher the spatial resolution. So this looks like a bunch of information, but again, the board does not ask us to get really in-depth on each one of these, so I want us to just have the terminology related to these things. Okay? And kind of the umbrella term that we use when we're talking about this kind of stuff is informatics, right? And we would call that the collection, classification, storage, retrieval, and dissemination, right? The sending this stuff out of any kind of recorded information, right? So every time you send your friend a text message, you are working in the realm of informatics. Anytime we send a doctor an x-ray, we're also working in the area of informatics. Pretty much our entire life now is informatics, basically, right? In radiology, we're going to be using a whole bunch of different kinds of medical information systems, including our cell phones, probably. I mean, I've worked at hospitals where we are texting each other constantly to coordinate care, right? So there's a bunch of different ways we can use this stuff. There's good ways and bad ways. DICOM, Digital Imaging and Communication in Medicine. And this was a universally adopted standard for medical information exchange. This is how PACS systems work. They have a DICOM in which they communicate the image data in. Now, even though it's a universally adopted standard, the standards themselves are not universal. So that's kind of confusing, right? Because it's going to be vendor-specific and typically year-specific, right? So McKesson's going to have their DICOM 2012, right? And they'll probably have to update that standard at some point. Their DICOM may not necessarily communicate with another DICOM. It may partially communicate. Like it may transfer all the images, but none of the attached data, none of the information about the patient. So be aware that even though DICOM is fairly universal, it still has some vendor-specific things about it, and the vendors want it that way. They want it to be a pain in your butt to change your PACS, right? Because then you have to, it's going to make you rethink, do I really want to pay less money for a PACS and knowing that I've got to change out all the informatics that goes with that, right? HL7 is actually universal, right? So these were standards that work to organize transmission of data, typically from like your X-ray processing, your digital processing center to your PACS, right? So, for example, from my CT scanner to PACS. The CT scanner is going to be connected to PACS over an HL7 connection, and this is actually a universal connection. So my CT scanner or your X-ray processing station can be connected to just about any kind of PACS because HL7 is universal. And it will also communicate with your RIS, like so your EMR will send information to the X-ray system. So if you don't have to manually enter stuff before you scan your image, that's because the HL7 is operative, right? Some things don't talk to each other. Like some electronic medical record systems do not communicate to the image processor. Do y'all have any clinical sites where you have that problem? You have to manually enter things. Mm-hmm. That's because they have probably the HL7 is active and it's a universal standard, but for whatever reason, they're having a difficult time getting the RIS or the EMR to communicate over that HL7. Does that make sense? Okay, I know I'm using a whole bunch of, it's going to start to sound like alphabet soup here for a sec, but just know that HL7 is a very broad, universal thing, and most EMRs and most PACSs should be able to connect to a scanner over the HL7 or a processing station over the HL7. That also means that, say, I had difficulty communicating with someone else's PACS. If I had a way to communicate, to send stuff directly from the processing station to their PACS over the HL7, I could. Right? So even if I can't get the PACS systems to communicate because their DICOMs aren't the same, I can probably figure out a way to patch in and send directly from the processor over an HL7. Right? Some troubleshooting is possible there. PACS is going to be a picture archive and communication system. This is broadly defined as the technologies necessary for storage, retrieval, distribution, and display of images. PACS is what we work with a lot, right? I can have PACS on my phone. I can have PACS in the OR. As long as there is a server that retains the picture archive, everything else is normally a client-based, right? So I'm not necessarily going to go into the server closet and try to pull up the images. I'm going to be sitting at a computer somewhere in the facility and access the PACS server via the client software, right? And that client software can communicate directly with the PACS. A RIS, a radiology information system. A lot of times this is a part of your EMR. So like for Epic, it has a RIS, I think it's called Radiant, right? That's the RIS. What it means is when a doctor orders a CT or X-ray chest over the EMR, it goes through over to the RIS. Now the RIS is going to say, hey, you have an order for a X-ray chest, right? And when you click in that you're going to get that patient, and a lot of times it starts a timer ticking. So when I think RIS, I think management. I think middle management. They sit there and look at the RIS and try to figure out how quickly are we doing our X-rays, why did Mrs. Smith have to wait so long, that kind of terrible stuff that middle managers do, right? I had a middle manager that I worked with that he would sit and stare at the RIS. He thought he was so smart, and he would wait until inevitably workflow slacked off in CT around 2 in the afternoon, and as soon as everyone started getting off from work, they all started going out and like getting drunk and having car accidents, you know? So he would sit at the RIS and see that our numbers were low, and he would send people home, and then inevitably an hour later they would have to call in the call tech, right? So just be aware that these things they're out there, they actually affect our lives, right? In very realistic ways, and the RIS is primarily used for scheduling patients, storing reports, patient tracking, protocoling, and billing, and then kind of hidden in there is workflow, right? Questions about that? Okay. Oh, there's a bunch of miscellaneous stuff that we could talk about for healthcare informatics. There's a hospital information system, there's clinical information systems, there's a computerized physician ordering system, CPOE, and a lot of times these can make things kind of confusing because it'll be an inpatient a lot of times. The hospitalist ordered an X-ray of the chest. It's going to have the CPOE is going to associate that with like the chief hospitalist name a lot of times. Like it'll have the ordering physician's name somewhere, and then it will have kind of his supervisor somewhere else. And so it will make the document very, very confusing to look at. And if you have questions about the order and you try to call the chief hospitalist, he's going to say, he or she will say, I don't know what you're talking about, right? That must have been someone else that ordered that, right? So just be aware these computerized physician ordering systems have glitches in them. Or physicians may enter the data incorrectly, right? If you all have had any, time working with physicians, you know that they're not that interested in any of this crap, right? They feel like it gets in the way of their work, and they're not interested in learning about it. So as a consequence of that, we get crazy orders. Like CT chest without, and they meant, oh, I wanted a chest X-ray, right? You see that kind of stuff. A lot of times that's because of this computerized physician ordering system. An electronic health record and an EMR. EMR is kind of the big term that everyone's talking about right now because the Affordable Care Act requires EMRs now. So for better or for worse, they're here with us to stay. So, review question. Information used for scheduling patients, storing reports, patient tracking, protocol, examination, and billing. Where is that going to reside? In the RIS. Good. The Radiology Information System. So that is it for that slideshow.